In this section, I'd like to show the relation between the force and the potential energies. Potential energy is related to the work. Work is equal to minus delta U. So minus like a U sub 2 minus U sub 1. The work also can be calculated F sub x times the delta x. So these two is exactly equal. So this means F sub x dx delta x is equal to the delta U. So if you divide it by the delta x, so F sub x equal minus delta U over delta x. So if you take a limit of the delta x to the 0, so F sub x is equal to minus du dx. So using the derivatives of the potential energies, we could derive the force. In the case of the 3 dimensions, again we can express F times delta R. This is actually the work, and the work is equal to minus delta U. So this is scalar product. So work could be expressed Fx delta x plus F sub y delta y plus F sub z delta z. You can calculate. So from these equations, these two equations, you can find F sub x delta x plus F sub y delta y plus F sub z delta z equal minus delta u. So if delta y equal delta z equals 0, so in this situation F sub x delta x equal minus delta u. So from this F sub x is minus round u round x. 3 independent variables, x, y, z. Z is the independent variables. The variables. So, but in this situation, y and x doesn't change. So, from these conditions, you can easily find out this f sub x should be expressed as the partial derivative with respect to x. Also using the same expressions, f sub y is a partial derivative of u with respect to y. F sub z, negative sign, don't forget, round u, round z. We have these relations. Once we know the potential energies, you can derive the force from using these equations. Okay, this is the equation I derived in the case of the 3-dimensional case. So if we have a potential energy curve, the springs, U equal 1 over 2 kx squares. Total mechanical energy is given by 1 over 2 mv squares plus 1 over 2 kx squares. So first part is a kinetic energy. Second part is a potential energy. In this energy diagrams, we draw the potential energies. When the particle has a total energy of the E, this is total energy, is a K plus U. And K is a 1 over 2 mv squares. This is always positive quantities. So K have to be the positive quantities or 0. In the case of the V, the velocity becomes 0. It is still possible. But always K is a positive or 0. So K is changing with the position. This is the maximum K is obtained. Particle come to this point, K is 0. So when the particle is coming to this position, it is not possible because the K becomes negative. So particle cannot get into this region. This is forbidden regions. Region to enters. Also same reasons. Forbidden regions. These regions between the two forbidden regions we called allowed region to move. As I explained, the force can be calculated minus round u round x. So at the bottom, this position, actually f is 0 because the derivative with respect to x is 0. So force is 0. So total amount of the force is 0 at the bottom. We call that this is equilibrium point because the force is 0. When the particle is moving to the, for example, this position, what happens? F is calculated minus round u round x. So round u round x, these positions, we could consider the tangent lines. So round u round x, this is negative quantities, negative slope. Then negative quantity times negative sign. So force becomes positive quantity. So at this position, applied force on this object is directed toward the positive direction. So particle is moving to the positive direction. When the particle is coming to this position, you could calculate f is minus round u round x. So consider the slope. This is positive. Slope is positive. So force is a positive times negative is negative. So applied force becomes negative direction. So particle is making the oscillational motion. So we call that this position, equilibrium point, is a stable point because the particle is oscillating around the equilibrium point. Okay, so we have two types of the stable and unstable equilibrium point. As I explained, at the bottom of these regions is a stable, but the top of the position. So as I explained, we should calculate round u round x. And then this point, actually the slope negative. So round u round x is negative. So this means force becomes positive. So if the particle is moving to this position, applied force is directed the positive direction. So when the particle is moving to this position, then the force applied force is the positive direction. It's moving away here. If the particle is coming to this position, slope of the tangent line round u round x is positive. So force is negative. So this is the direction of the force. Then the particle is moving away from the equilibrium point. So going down. On the highest point of the potential energy, of course round u round x is 0. So force is 0. So we call this point is the equilibrium point. But when the particle is moving away from the equilibrium point, this particle is start moving away from this point. We call this is unstable equilibrium point. But the bottom of potential energy curves, particle is making the oscillation motion around this region. This is stable equilibrium point. So we have two types of the equilibrium point. By looking at the shape of the potential curves, we could judge if the equilibrium point is stable or unstable. Then in the last topic in this session is a conservative or non-conservative force. So conservative force is example is gravity's conservative force. It can be expressed as a difference between the initial and the final value of the potential energy function, and it is reversible. It is independent of the path of the bodies and depends only on the starting and ending point. When the starting point and ending point are the same, the total work is zero. This is the conservative force. So these four conditions have to be satisfied by the conservative force. For the non-conservative force, example is the frictions. When we consider the friction, the object is moving on the path. This is the frictional force is acting on this object is moving on this path or moving to this path. So initial point and ending point is exactly the same. But total amount of the work done by the friction is different. So work done by friction is depend on the path. So in these situations, we call the friction is a non-conservative force. Then change of the energies. The total work done by the conservative force and the non-conservative force can be calculated sum of the two work. Work done by the conservative force double sub-conserve. Work done by the non-conservative force is double non-conserve. And the conservative force is expressed as a change of the potential energy U sub 1 and U sub 2. So U sub 1 minus U sub 2. Okay, and the work energy relations, total amount of work is equal to the change of the kinetic energy. This is the work energy theorems. Then this is equal. You can express conservative force. You can substitute here. U sub 1 minus U sub 2. Then K sub 1 moving to this, U sub 2 is moving to here. Then we have a relation. K sub 1 plus U sub 1 plus W non-conservative equal K sub 2 plus U sub 2. So total mechanical energy changes due to the non-conservative force, existence of the distance. For example, we consider W non-conservative is negative situation, consider like frictions. So particle object is moving to the right with the speed of the v. Then frictional force is acting. This is friction acting on this object. Total energy at this point, energy is just only kinetic energy 1/2 mv squares. So because of the existence of the frictions, speed is decreasing. And finally it's going to, we expect the v equals 0, stop. Particle is going to stop. In this situation, the energy becomes 0. So K sub 1 plus W non-conserve equal K sub 2. And K sub 2 is 0. So K sub 1 is exactly equal to this positive quantities. So W non-conservative is equal to minus K sub 1 when the object is going to stop. Okay, when we consider the frictional force, total mechanical energy cannot be conserved. So we have to consider the contribution from the non-conservative force. Okay, this is the end of this session.